Now today we are going to do section 6.4, arc length and surface area. I have a fly flying around. The arc length and surface area are both specific formulas of some function. In the way you calculate arc length and surface area is just plug in the formula and then it'll pop right out. So what we're going to do in this section is I will explain how the formula is derived, and then you will do the examples by plugging in the suitable information into the given formula, and then watch the results pop out. Okay, so it's going to be fairly short. First, let's talk about what is arc length. Arc length is the length of a graph. For example, let's look at this graph on the page where you see that there is a function that goes up and down. Well, the question is, how long is that line? Well, if the line was straight, then we'd be able to calculate it directly by the Pythagoras theorem. But the line isn't straight, so now what? Well, what we're going to do is the Riemann sum. And just that, in other words, calculate a little bit at a time and then add it all up. So to do that, let's go to the next page. What we're going to do is look at this graph right here. This is a simulation of a tiny little bit. Okay, we're going to start doing a small amount, and where we calculate the x-axis difference as delta x and the y-axis as difference as delta y, and imagine it to be very, very small. Okay, because the smaller it is, the easier it is to approximate. And what we're going to do is calculate the hypotenuse. I suddenly forgot what that's called. Just a slanted line from that is from this point. Well, whatever. The point is, yeah, that will approximate the graph, and therefore, I suddenly forgot. Is it called hypotenuse or whatever? The point is, so we're going to calculate what delta x squared plus delta y squared. Why don't I just draw this out? Okay. So let's say you have some kind of curve, right? And I want to know how long it is from here to here. But it's bent, so it's hard to tell. And then, so what I'm going to do is draw a straight line across, which is shorter than the original, but we'll approximate it that way as we make the calculation smaller and smaller. It'll be more accurate. So this distance is called delta x, and this distance is called delta y, and the hypotenuse is called delta x. What is this called? The length of this line segment. Your book doesn't even say. Well, whatever. The point is the hypotenuse. We'll just call it that for now. Is called by the Pythagoras theorem. Of course, is a squared plus b squared times the square root. Okay, delta y squared. And remember, delta x is one variable. It just means the change of x versus the change of y. And by the Pythagoras theorem, it is equal to the square root of this stuff. So now that we know that, and that's the total, that's the length, all right? And then we are going to do, what we're going to do is change this equation to look something like this. We're going to factor out this thing. Okay, and to put it outside the square root, so that equals to delta x. We'll plug it out of there, and then this is 1, and then we have to divide by delta x down here. The square root is still here. That way this comes out to be the same. And then what we're going to do is look at this thing. What is delta y over delta x? By that is the same as by the mean value theorem, or just by looking at it, the delta y by delta x is the slope, right? And what's the slope? Well, it's the derivative. So we can say that this equal to delta x square root of 1 plus the derivative of f. This function is f at some point in here, okay? And by the mean value theorem, which states you can find some point where we'll call it xi. we'll call this point xi. This is a little thing in all of it. Xi, well, your book even put a star there. I guess that's okay. Because this is xi, okay? And then this is xi. Now this is xi minus 1, and this is xi, which is fine. Okay, so then the primed, the derivative squared to become delta y over delta x squared. The point is that's the derivative of some point in here. Now having said that, then that's just one section, okay? Now we're going to add up all of it. Let's add up all of them. Then as you can see here, if you add up all of them, then it becomes, as we've been doing, the adding up, it becomes the integral. Okay, let it go to infinity or something. That equals to the integral of the whole section, and then and delta x becomes dx. And this, what's inside, is 1 plus the f prime of x squared. Okay, and that's how the arc length formula is derived. So let's look down at the arc length formula. The arc length formula is very straightforward. If you have a function, okay, and you have to calculate the length of that thing from a to b, from where x is a, x equal to a to x equal to b, you just plug it into this formula and out pops your result. So, and that is how it's derived. So please do example 6.18. Yeah, you plug in the function, and then usually to actually do the integration is impossible or almost impossible, so you just use the definite integral calculator and let the answer pop right up. And in fact, sometimes even the infinite calculator can't do it. So I picked problems for this homework, all the problems that the calculator can do. There were some of them the calculator couldn't even crank it up. So then I skipped those problems because there is no reason to do that. So please do, for homework, for arc length, please do examples 6.18, 6.19, and 6.20, which is when you, instead of doing dx, you're doing dy. You know, the function is expressed instead of x is expressed in terms of y. It doesn't matter which way it's expressed, the integration works exactly the same way. It's just that you replace x with y. And so that's 6.20. And let's go to page 675, where we are going to do the area of the surface of revolution. That is, if you have some object that you're spinning around and by some curve, see the curve on one side and then you left side, and then you see that when you spin it around, it creates some kind of solid. The question here, now we've been calculating the volume of that thing, but now the question is, what is its surface area? Yeah, being that object is bending all over the place, you can't calculate it directly, but we are going to approximate it again with the Riemann sum principle. To do that, we have to first know how to calculate the area of the approximation. We'll approximate it with something like this, okay? A small piece that's very, very thin, but looks like this. This is called a frustum. Well, at least that's what your book says, see? And so we're going to approximate that solid with a whole bunch of little thin things like this. This one looks really thick so that you can see it better, but in reality, we're going to make it really thin in order to have a good approximation. So this thing is called a frustum, and then the frustum, of course, is calculated by the what is this thing called? Well, I don't care what it's called, but you find the surface area of this, a cone, I think, ice cream cone, right? So you find the area of the cone, then cut off the top, which is a smaller cone. The surface area of the cone, just the lateral surface, that is the side, not counting the bottom, is given by some formula called pi rs, where s is the length of the slanted side. That was calculated back, a couple of classes ago. I don't know, I don't know which class taught you this, but that was done before. Okay, so we'll just accept that the area of the slanted thing is pi r s, and similarly, therefore, when you do subtraction of cutting out the top of the cone to get the frustum, the area is called, look at the bottom, pi times r1 plus r2 times L, where r1, r2 is the two radiuses, the top one and the bottom one, and L is the slanted distance of L is the slanted distance of your frustum, okay, the side, how long it is on the side. Now your book decided to redo the math to prove to you how the frustum area is calculated, but that's already been done and we are not going to go over it again. So we'll just go by the fact that the area of the frustum has that particular formula, and then so that we can get to doing the Riemann sum. So now we're going to do the Riemann sum. Then let's calculate the area of this whole thing. So by the formula, then for the frustum, the surface area of one of them, okay, we're going to build a whole bunch of these things, and then see there's one frustum that approximate a small area, small distance, delta x, and then eventually we'll add it all up with integration. So we'll build our Riemann sum and then add it all up like we've been doing this whole time in the last few sections. So the surface area of one of the frustums, one little one, which is pi times r1 plus r2 times the length, the side length, okay, which is L, and then we will calculate it as so r1 is equal to the f of x before that, so equals to pi times f of x I minus 1, okay, that's the first radius, see, yeah, anyway your book shows that, and then plus pi r squared, no, what is this, it's just r1 plus r2, there's nothing squared about it, okay, plus f of the second one, r2, which is f of xi, and then times the square root, the slanted L, which is the slanted length, is delta x squared plus delta y squared of this thing that takes the square root, and yeah, that's about it. Here's the parentheses, so then you can see that that's what we're doing, okay, the f, and you can see the radius here, look at the graph, then x minus 1 is the previous height or radius of the frustum. The frustum is sideways, so the radius is the height, kind of. And anyway, so once we've done that, then the rest is just we do manipulating some algebra. So just like before, this equal to, first that thing turns into this part here turns into this thing right here, see, the exact same thing. So this part we'll write it like this, equals to delta x, you factor the delta x out, so you get 1 plus delta y over delta x squared, and which then equals to same as this, right, is equals to some kind of a derivative. This is just the derivative at the point. So delta x 1 plus f prime of xi. Yeah, some kind of star here. That the star means the xi is between xi and xi plus 1, and that's done by the mean value theorem. But the point is, this thing is going to be, yeah, that's how it works out, just like this one. And then in the meantime, this part is being that if you have f, x, and I, and the one before and the one later, so we're gonna just combine those as what was that? The intermediate value theorem. So the intermediate value theorem says we can just combine these things and call it one of them, okay, the average value. So we'll pick another function. This is the same as f2 of something else. 2 of f, some value in here, xi 2 stars, okay? Where two of them is the same as this thing, these things added together, and that's by the intermediate value theorem. Is because there's 2 of them, you just figure out the average of these 2, and then multiply by 2. That's all, okay? And then so next, so now we have, what do we have? So if we sum that up, that would be equal to so next, the surface area is equal to of just one frustum. Okay, we do one at a time. Rewrite this thing equal to pi times 2. Then f of xi, where this is a point between xi and xi plus 1. And then times delta x times this thing right here. 1 plus f prime of xi, 1 point, and squared. Now we have stars on top because these two, this one with 1 star is different from this one with 2 stars. But it's of no consequence because we're letting delta x become very, very small, which means that these 2 values are all going to the same point, xi, anyway, right? It doesn't matter that the different, they're all getting squeezed in. And then so at this point, then we are ready to do we'll sum this thing up with a Riemann sum, which means that becomes the definite integral, okay, when you sum it up. That would, so the definite integral will be integrating from a to b, 2 pi f of x, and then the delta x becomes the dx over here. And then the integral of 1 plus f prime of x squared. And that would be the formula, general formula for deriving the surface area. Now, as you can see, the surface area is a whole lot harder than just the arc length because you have to take the square root. The arc length already have to take the square root of something, which doesn't make it easy. But the surface area, you actually have to multiply by f of x too. So that makes it even stiffer. And that's why sometimes when I try to run the definite integral out calculator, even it couldn't get it. It just sat there and spun around. So at times I find that there's a calculator that your book offers, a definite integral calculator, that sometimes seems to work better than the one that I have been using. So I will put your book's calculator, definite integral calculator, in the homework assignment. I hope I remember to do that. And so that you can try either one. If one doesn't work, try the other and see which one can come out. But mostly, I only pick the problems that integral calculator does work, so it should be okay. So with that marks the end of deriving the surface area formula. As you can see, in general, what you do with this kind of problem is you just derive the Riemann sum by approximating a very small chunk, and then that comes out with a formula that's good for everything. Okay, there isn't any problem that this doesn't work. Well, of course, then you might end up being stuck that your calculator can't come up with the answer, but at least on principle it works. And with that, please do example 6.21 all the way to the end. Okay, the warning of doing this kind of problem is, number one, you must pay attention which way dx is going. That is, and also pay attention to Pay attention to which way your solid is spinning. Don't spin it around the wrong axis, which I have done, and then your answer is complete garbage, right? So just pay attention to some of the details, and then it should come out okay. So please do the rest of the examples all the way up to up to example 6122, I think that is. Some of the problems are calculated in terms of y. Again, that makes no difference. We don't care if it's x, y. You just have to make sure your endpoints are going to the right place. That if it's calculated in terms of y, but your problem is presented in terms of x, then you just have to transfer x to y. All right, so that is that. So for homework, please do page 682, 682 problems 171, 175, 181, 185, 193, and 199. And these problems are very easy to do, except for the part where you have to plug in the integral calculator. You just make sure that you got in the right axis, okay, spinning around the right axis, and your dx is correct. Which way am I integrating? That sort of thing. And so please go do your homework, and when you're done, I want to talk about some of the homework. Now that you're done with the homework, let's talk about some of the problems. 171, which is y equal to x to the power 2/3, etc. You're supposed to calculate the arc length. So what I did is I plugged it into the arc length formula. Y is equal to x something. So everything's straightforward. I integrated with respect to x and then plugged it into the calculator, and out pops that answer, which turns out to be right, according to the back of the book. And next problem 175, same thing. Okay, I wrote down the problem and then plugged it into the calculator, and out pops the result. You see, it's a one-line answer. Very, very quick. Okay, so that's that. Next, let's look at the next problem, 193. Okay. Next problem is 193. All right. So you have to spin around the straight line, 193, which means that if you're going to spin around the straight line, that just creates a regular cone. Okay. You don't need integration for that. But I did it anyway, and so I plugged it into the formula, and out comes that answer, which is again correct. So that's 193, and then lastly 199. Which is anyway, this one you have to spin around the y-axis, so I guess you have to remember that. Oh yeah, so the only difference of 199 is that you're spinning around the y-axis, I guess, so everything has to be in terms of y. So you just plug x in terms of y equal to x squared is what you're given, so x equal to the square root of y. And then you integrate it on the surface area, and then everything popped out once you plug it into something. And that's about it.